All right, let me just start again. So for power series, we talked about this convergence. We talked about this convergence last time. Its convergence actually consists of three cases. First case is when it converges only at one point, x equals a. In this case, we get a bunch of zeros. And then the second case, it converges at only on an interval I with some radius r, okay, centered at a. Now the third case is when the radius r is actually infinity, i.e., it includes every x, it converges for x. And then what is you need to be careful is in case two. In case two, there should be anything can happen at the case two. Okay, it can converge, it can diverge at any of this boundary. And then we give several examples of power series and how to determine its radius of convergence and the interval of convergence. Okay. Now, if the power series converges on a finite interval, then you need to actually check the convergence at the boundary. Okay, you need to check the convergence at the boundary. Okay, now let's see starting in power series. Let's see power series, and then how to determine its radius of convergence. All right, let's see this example. Let's see this example. Negative 1 to the power n, x to the power 2n over 2n factorial. So the general term an is negative 1 to the power n, x to the power 2n over 2n factorial. In general, to determine the radius of convergence of power series, what test do we usually do? Do we use? The most useful test for power series is ratio test. Okay, ratio test or root test. In general, ratio test is more often. Okay, so we actually use ratio test, and then find the next term an plus 1. Replace n by n plus 1. Replace n by n plus 1. 2n plus 1 factorial. Then we take that ratio, and see what we get at that ratio. Okay, so that ratio, an plus 1 over an, absolute value. Now here are the alternating factors. Let's just find alternating factor negative 1. Do some algebra. It's 2n plus 2 over 2n plus 2 factorial. So this is an plus 1. And then for an, when we divide by an, what we do is we flip the denominator numerator, flip an. We get negative, so this is negative 1 to the power n. Now numerator becomes denominator. Denominator becomes numerator. Now negative 1 to the power n, its reciprocal is itself. Okay. Now we take absolute value. Now negative 1 to some power, it's plus minus 1. When we take absolute value, then we get a 1. So this is alternating factor just gone when we take absolute value. So this will be x terms with x terms. Then we have 2n factorial over 2n plus 2 factorial, also value. Now x use power rule. This we get x, squared. Okay, 2n cancel 2n, so we get x squared. Now remember, 2n factorial is 1 times 2 times 3 all the way to 2n. 2n plus 2 factorial is 1 times 2 all the way times 2. 2n times 2n plus 1, then times 2 plus 2. Okay, so Jesus, what happened? Okay, so if we do some cancellation, the factor 1, 2, 3 all the way to 2n actually cancel itself. So we have 1 over The remaining factors is 2n plus 1 and 2n plus 2. Okay. This is positive. Now x squared is non-negative, so it's the absolute value itself. Now remember, by ratio test says if this ratio is bounded by 1, limit of this ratio is bounded by 1. Limit, let's find limit. Now for any fixed x here, limit n approaches infinity, which is an plus 1 over an. So for fixed x, for any x, we fix it. For fixed x, limit, this absolute value will be limit x squared times 1 over 2n plus 1 times 2n plus 2. Now as n approaches infinity, now x is a constant here. As n approaches infinity, you see 1 over that factor denominator approaches 0. Okay, the denominator can be arbitrarily large. So this is actually x squared times 0. So we got actually 0. Now 0 is always less than 1. 0 less than 1. So by ratio test, the series converges for any fixed x. The series converges. So it has nothing to do with x value. Converges for any x. i.e., the radius of convergence, the interval of convergence. Now it's easy. Interval of convergence. In this case, it's negative infinity to infinity. The radius, radius of convergence is actually infinity. Okay, infinity. Okay, let's see this example. This example, 4x plus 1 to the power n over n squared, n from 1 to infinity. This power series. Okay, now as I mentioned earlier, we use a ratio test to determine its convergence. So this an, the general term is denominator n squared, numerator is 4x plus 1 to the power n. And then we find their ratio. Replace n by n plus 1, the next terms, to the power n plus 1. And then take their ratio. Okay, the ratio of this. Take the ratio. Okay, take the ratio. And this will be, so we keep an, and then flip, keep an plus 1, flip an. Okay, so if you do cancellation, don't forget this absolute value, cancellation. Now 4x plus 1 to the power n plus 1, cancel a factor 4x plus 1 to the power n. Then we get 4x plus 1 absolute value, times n squared over n plus 1 squared. And then we need to find this ratio, limit n approaches infinity. So n approaches infinity, an plus 1 over an, which is limit. Here x is fixed, n approaches infinity. Now you can use L'Hopital's rule. This is very easy. Now 4x plus 1 is a constant. You can factor it out. Limit n approaches infinity. Now use L'Hopital's rule. You'll find this is actually use L'Hopital's rule, n over n plus 1. This limit is 1. So this is actually 4x plus 1. This limit. Now by ratio test says if the series, if 4x plus 1, this ratio is less than 1, then the series converges. The series converges absolutely. Now if the ratio is greater than 1, the series diverges. So we don't need to consider the case when x greater, this absolute value greater than 1. Then the series converges absolutely. Absolutely. So and then we need to consider the boundary. In this case, we work out is actually bounded by 1, bounded by -1. So then this get 4x is bounded by 0 and -2. Then x is bounded by 0 and -1/2. Okay. Now we need to consider what happens at the boundary. Okay, at the boundary. So if now we also need to, because the ratio test fails when the ratio is 1. Okay, so we need to check what happens when the ratio is 1. If 4x plus 1 equal to 1, ratio test fails. We don't know whether it converges divert, so we need to check. So i.e. x equals 0 or -1/2. So if x is 0, then the original series, remember the series is 4x plus 1 to the power n over n squared. This will be the series n squared, 1 over n squared, okay? X 0. Now this n from 1 to infinity. Now this actually converges by p-test. Converges by p-test. Now the power of n is 2. P equal to 2 greater than 1. Okay, it converges. Actually, we know this thing converges to pi squared over 6. So when x is 0, it converges. Then what happens when x is -1/2? If x is -1/2, let me see this series 4x plus 1. 4x plus 1 will be -1. Okay, plug in. So this will be 4 times 1/2, -2. So it's -2 plus 1, -1. -1 to the power n. N from 1 to infinity. Now this is the alternating series. Converges. It also converges. You can easily use alternating series to conclude this converges. Okay, by alternating series test. So it's decreasing limit 1 over n squared upper 0. Or you actually take the limit, or you take absolute value to conclude that this converges absolutely. Okay, because 1 over n squared converges by p-test. So it converges because it converges absolutely. Okay, so at the both of the two endpoints, it converges. Okay, so the series, so the radius, the interval of convergence of the series for x plus 1 to the power n over n squared, n from 1 to infinity, is -1/2 to 0, both including the boundaries closed at the two boundaries. Okay, now the radius of convergence, radius of this interval, we have the interval -1/2 to 0. Its interval is this. The radius is half of the length. Okay, radius of convergence is actually 1/2 the distance, 0 minus -1/2. So we finally get this is actually a quarter, half of the distance, okay, half the distance. Okay, more examples. Okay, this series. Now what we do is we find an, the general term. Now we use the ratio test. Find the next term, an plus 1. Replace n by n plus 1. Everything keep fixed. n plus 1 times 2 to the power n plus 1. And then take the ratio, an plus 1 over an, take the ratio. Is we flip an, keep an plus 1 fixed. And then the alternating factor, we can forget this alternating factor here because alternating factor when we do absolute value, this is just gone. So there's no longer alternating factor because it's plus minus 1. When we take absolute value, it's just 1. Okay, then we do cancellation. So you see we have a 2 to the power n. We have a 2 to the power n plus 1. Okay, so they cancel out each other. So we have 1/2. Okay, we have 1/2. Now x plus 2 to the power n plus 1 cancel the power x plus 2 to the power n. So we have x plus 2. Now we have, we have n over n plus 1 is remaining. Now don't forget the absolute value. Okay, this is the absolute value. So limit, now we take a limit n approaches infinity. Ratio test says if the limit is bounded by 1, then it converges. Now x plus 2 here is fixed. So when we take limit n over infinity by L'Hopital's rule, or it's very easy, you find this limit is actually n over n plus 1 is 1 is limit. So this is the limit that we get of the ratio, limit of the ratio. Then ratio test says if less than 1, the series converges. Okay, now if the ratio equal to 1, we don't know. If the ratio greater than 1, it diverges. Okay, so we only need to consider the case when this equal to less than 1 and equal to 1. Okay, now in this case, x plus 2 less than 2, x plus 2 less than 2 bounded by negative 2. So get x is bounded by 0 and negative 4. Okay, if so we need to look at the boundary and see what happens. Equal to 1, because here the ratio test fails. We need to check, we need to use more information, i.e. x equals negative 4 or 0. If x is negative 4, then the series becomes, you check what happens for the series. N from 1 to infinity, negative 1 to the power n, x plus 2 to the power n over n times 2 factorial. Now x is negative 2, so you negative 1 to the power n. Negative 4 plus 2, you get a negative 2 to the power n, 2n, n from 1 to infinity. Negative 1, so times negative 2. So you get actually, this is the 2 to the power n over n times 2 to the power n. N from 1 to infinity. Now 2 to the power n cancel 2 to the power n. So we get this is the 1 over the n from 1 to infinity, which is the well-known in the harmonic series. Okay, the harmonic series. Also, when the diverges, harmonic series diverges. So when x negative 4, the series diverges. Okay, if x 0, then we have the series now becomes now plugging x by 0. So this negative 1 to the power n, 0 plus 2, which is 2 to the power n, over 2 to the power n from 1 to infinity. Now 2 to the power n cancel 2 to the power n, then we get this negative 1 to the power n over n from 1 to infinity. Now this is alternating sum of reciprocal of integers. Okay, this converges. Okay, converges by p-test, by alternating series test. Alternating series test. The terms, they are alternatings, and then it's decreasing. Y over n is decreasing. and the limit 1 over n approaches a, the limit is 0. 1 over n, limit is 0 as n approaches infinity. Okay, actually we know it converges to this equals to negative ln 2. Okay, this converges to ln negative 2. Okay, so we know it converges at 0, diverges at negative 4. So we can conclude the interval of convergence. The interval of convergence of the series negative 1 to the power n x plus 2 to the power n over n times x 2 to the power n is, now it's negative 4 to 0. At 0 is okay, so it's closed interval at 0. Okay, at negative 4 it diverges, so we just have open at 4. Okay, open at 4, open at 4, then closed at 0. Okay, so it's a half open and a half closed. Okay, so this is this example. Okay, maybe one more example. This example, n from 0 to infinity, x to the power 2n plus 1 over 2n plus 1 factorial, negative 1 to the power n. Okay, now this general term an is negative 1 to the power n, x to the power 2n plus 1 over 2n plus 1 factorial. Okay, now we use ratio test. It's power series, we use ratio test. Now next term is replace n by n plus 1. Two times n becomes 2 times n plus 1. Now 2 times n plus 1 becomes 2 times n plus 1 factorial. Now you take the ratio an plus 1 over an, absolute value. Now here the negative alternating factors, negative 1 to the power n, just gone. Okay, so we get this is the x 2n plus, now you do some algebra, 2n plus 1 with times 2, so you get a 2n plus 2 plus 1, you get a 2n plus 3 over 2n plus 3 factorial. Flip denominator with flip denominator numerator. The negative 1 factors are gone. And then you do algebra, use power. Now x factor, then we get x to the power, 2n plus 3 minus 2n plus 1, you get actually 2. And then the other factor you get, this is 1 over 2n plus 3, 2n plus 2. So factorial will write down according to the definition of factorial, okay? And then you do a cancellation, you see what is remaining. You find this thing. This actually non-negative, so its absolute value is the self, okay? Now limit n approaches the infinity of this ratio. This will be limit n approaches infinity. X squared 1 over 2n plus 3, 2n plus 2. Now x is fixed here. So when we take limit, we just factor it out. Now the remaining thing has limit 0 because the denominator can be object large. Numerator is a fixed 1, it's 0. So this we get, this is the 0. Now this is of course less than 1 for any x, It has nothing to do with the x. So we can conclude by ratio test. For any fixed x, it converges, i.e. it converges for any x. By ratio test, the series converges. The series converges for any x, for all x. Now its radius of convergence is infinity. Okay, radius is infinity. For x, interval of convergence is negative infinity to positive infinity. The radius is of course infinity. Okay, now this is the how we determine the convergence for power series. Okay, now we go to the next section. Representations of a function by power series. Representations of functions. Representations of functions as power series. Oops. Oh, sorry. Okay. Okay, I need to make this smaller a little bit. Oh, Jesus. Okay, all right. Representations of a function as power series. Representations of functions as power series. Okay. Now the idea is we can use polynomial to approximate a function. Okay, a reasonable function. If this function is reasonable or nice. And a polynomial is polynomial is a special case of a power series. So actually we can approximate a reasonable function by a power series. Okay, so so the idea is 13 types. So we have 13 type of functions. We can represent it, or you represent it by expand, or you expand it by. So then you get a power series. Or you use you view it simply as approximation. You simply view it as approximation. So for any continuous function, the key fact is for any continuous function on any bounded interval, you can approximate it by a polynomial. As how good you give any control, to any precise. Okay, this approximation you can approximate as any you can approximate a really good nice function by power series. Okay, the advantage of the right side is power series. The power series Cn x to the power n from 0 to infinity maybe. Now the right side is algebraic. Okay, algebraic, which makes it easy to deal with. For instance, it's easy to deal with differentiation. Okay, differentiation and integration. For instance, differentiation. It's easier to differentiate. Differentiation, integration. They are easy to deal with because we have power rule. Okay, and they are really good. Multiplication is algebraic, so it's so easy to manipulate. So this is actually really good once we have power series. Okay, for instance, the examples that we did is this we already did some examples. Okay, for instance, y plus x squared, etc., etc. This is the sum of powers of x. Now by geometric series, this is the y over the first term is y. Okay, so y is the first term. And we have a common ratio. Common ratio is you find the adjacent term, ratio of the two adjacent terms. Common ratio is equal x. So we can write down its sum by geometric series. Okay. Now here we assume x absolute value is bounded by y. X value is bounded by y. So this converges if x is bounded by y. Now we did many algebraic manipulation of this. For instance, if we differentiate, we get we did it actually last time several times. Differentiate with respect to x, term-wise. So in general we cannot, but here in this course we just assume we can do term-wise integration, term-wise differentiation. So without any problem, to get the left side we get a y. Now y we get a 0, x we get a 1, plus 2x plus 3x squared, plus etc., etc. This we get n x to the power n minus 1, n from 1 to infinity. So the term n equals 0 just gone. The right side we get d dx, 1 over that thing. So this we get 1 over 1 minus x squared. Okay. Here again, once again, x is bounded by y. X is bounded by y. Now, of course, we can integrate. You can also, of course, differentiate again to get a more complicated series. Now we can also integrate. Let's use equation y. Okay. We integrate equation y. Integrate both sides of equation y. Of equation y. Now we need to make sure when we integrate, we need to make sure we are, within the range such that this equation makes sense. Otherwise, it's wrong. So for instance, from 0 to t, y x power n dx. This will be 0 to t dx. Here t, we need to make sure t is bounded by 1. T absolute value of t is bounded by 1, such that this is within the range of this convergence. So it makes sense. So we integrate term-wise by fundamental theorem of calculus. The right side we get ln, by fundamental theorem calculus. Okay, you find its antiderivative. So the left side you get n from 0 to infinity, y over n plus 1, x n plus 1, 0 to t. The right side you get y minus t minus negative ln y minus 0. Now ln y is 0, so actually you get a negative ln y minus t is the left side. You do the algebra, you find when you plug in 0, you get a 0. This you get y over n plus 1, t to the power n plus 1, n from 0 to infinity. If you change the index subscript, if you change the index n from 0, when n is from 0, n plus 1, is from 1. So you can change the index. So this is n from 1 to infinity, n 1 over n times t to the power n, This is negative ln 1 minus t. So we get a power series representation of ln. So this is really important here. So you get negative ln y minus t is this thing, n from 1 to infinity. If you write down several terms, so it's t plus t squared over 2 plus t cubed over 3, etc., 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 etc. Now, if you let t be negative t, okay, so you get a negative ln 1 plus t replace t, be negative t. Then you get a 1 over n, negative t to the power n from 1 to infinity. So this is actually negative t plus t squared over 2, minus t cubed over 3, etc., etc. So if you multiply both sides by -1, then you get a then you get a positive 1 plus t is t minus t squared over 2 plus t cubed over 3 minus t to the power 4 over 4, etc., etc. Okay, here t is bounded by 1. Okay, so you see, we have a lot of flexibility when we deal with power series. We can easily find it's a derivative and antiderivative. Okay, now let's do this example. Do this example. Do this example. Do this example. Explain this 1 plus x squared, 1 over 1 plus x squared as geometric series. Represent this as power series. Now, what we do is we use geometric series. This is the 1 over 1 minus negative x squared. Remember, this geometric series a to the r minus 1, r from n from 1 to infinity. This is the a 1 minus r. Okay, here r is bounded by 1. So we can use geometric series expansion of geometric series. So the first term here, a is 1. We take a to be, what happened? Okay, we take a to be 1. A to be 1. And then r to be negative x squared. Then actually we get this. Okay, then what do we get by geometric series? This will be, the first term will be 1. The next term, we multiply common ratio. Okay, this is common ratio. We multiply the common ratio, negative x squared. Next term, we multiply the common ratio again, negative x squared, negative, we get a positive. We get a, degree 4. Then we multiply common ratio, negative x squared, and then we get this. Then we get actually, etc., etc. So it's alternating sum, okay, of the even powers of x, okay, so it's x to the power 2n, negative 1 to the power n from 0 to infinity, okay. So the right side, so here we assume x is bounded by 1, x is bounded by 1. So here, because here r is bounded by 1, then we get x squared bounded by 1, so we actually x value bounded by 1. So we get this power series representation. So we get 1 over 1 plus x squared, which is 1 minus x squared plus x power 4 minus x6, etc., etc. Here, absolute value of x is bounded by 1. Now, we do some algebraic thing. For instance, we integrate both sides with respect to x. Okay, integrate both sides. Okay, from 0 to t. Of course, when we integrate the range, the domain from 0 to t, the interval should lie in bounded from -1 to 1. Okay, so this we get integral this 6 multiply, okay, n from 1 to infinity, 0 to infinity dx, 0 to t. Now, as I mentioned earlier, in this course we can always switch term-wise integration. In general, we may not, but in this course, our functions are nice, so we can do that. X to the power 2n dx. Now, the left side, remember, we check the antiderivative table. This is actually in the antiderivative table. So this is actually arctangent. Okay, remember arctangent derivative from 0 to t. we applied fundamental theorem of calculus or Newton-Leibniz formula. Okay. Now, so this actually you get arctime of t minus arctime of 0. The right side you get from 0 to infinity. This is use power rule, power increase by 1 and then divide from 0 to t, from 0 to t. Then you get arctime 0 is 0, remember, arctime 0 is 0. So this is arctime of t. And then the right side, you use Leibniz formula, Newton-Leibniz formula. Now x 2n plus, when x is a t, it's just t to the power 2n plus 1. Now when x is 0, it's just simply 0, so we just forget 0. So we get a power series representation for arctime. Arctime. So t absolute value is bounded by 1. Bounded by 1. Oh, sorry, it's -1 alternating factor. Otherwise, it's wrong. Okay, fact. The above is still true. Fact. The above is true. It's the equation is still true. The above equation. Equality. Equation. Equation. The above is true. The above is true. Even if t equal to 1. T equal to 1. Okay. Now let's see what happens if we what happens at the boundary. Anything can happen at the boundary. Very often at the boundary, there are really interesting. Things happen. So let's see what happens when t is 1. Plug in left side arctime of 1. Arctime of 1, which we get pi over 4. Okay, pi over 4. The right side, what you get is you plug in t by 1. Then you get when n is 0, then you get 1. Okay. When n is 1, plug in n by 1, so you get 1/3. If you plug in n by 2, then you get 1/5. Okay. Now you see the alternating sum of the reciprocal of all the numbers 1, 3, 4, 5, 7, 9. The alternating sum of the thing actually equal to pi over 4. Okay, so we get pi over 4 equal to 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9, etc., etc. Now this formula was first discovered by Leibniz. Okay, now remember pi over 4. Pi is the area of a unit disk. Okay, pi is area of a unit disk. Pi over 4 is actually area of a quarter disk. Okay, so it's actually called a quarter circle formula. Leibniz quarter circle formula. Quarter circle formula. Quarter of a circle. Okay, the above is called a Leibniz quarter formula. This is really amazing. Okay, this is really amazing. Why? Why is it really amazing? You see, when we deal with integers, manipulating odd numbers, okay, by alternating sums, and then mysteriously, this is related with pi, okay? This is related with pi. And actually, this is actually only a piece part of a beginning of a big story, okay, in number theory, i.e., this is related with special values of L functions, special values of L functions, special values of L functions, Now, for instance, we mentioned earlier the Basel problem, which actually says the following: 1 over 1 squared plus 1 over 2 squared, 1 over 3 squared, etc., etc. Sum of the reciprocal of squares of integers. Now this actually again related with pi squared over 6. Okay, these two formulas are of the same flavor. Okay, they are from the same kind of both come from special values of L functions. Okay, even today there are also many open problems for in this area. Okay, for instance, even we change the number 2 to number 3, we don't have closed formula. We don't have closed formula for that. Okay, etc., 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 etc. So we know very few about this sum of a cube of integers. Okay, we don't have a closed expression. Of course, we can do it numerically, but we want a closed formula. Today, still we don't know. Open. This is open problem. Open problem. And actually, this is really beautiful area in mathematics. Okay, and this is a really beautiful part of number theory. One of the mathematician, German mathematician called Kronecker. Kronecker, he has a famous saying. He says this: God created numbers, all else is the work of man. Okay, Kronecker, famous Kronecker. God created numbers. Now you see, number theory is a really beautiful area. Create numbers. All else is the work of mind. Of course, this is the written in German. If you translate it, it looks like this. Translate it into English. Okay. Now, unfortunately, we cannot go too far in this area. This beautiful part. We will come back to our power series representations. Let's do some examples of power series representations. Power series representations. Okay. Example. Okay, integrate. Let's do this example. Find any derivative. Arctan x over x dx. Find any derivative. Now this turns out to be it's really difficult if you try to use the old technique. The old technique that we learned in chapter 7, integration by parts substitution. If we try to solve it, it's difficult. So here we will not do it. Now what we do here is we use power series to find a reasonable antiderivative. Remember arctan. We just find a power series representation of arctan. Arctan x power series representation is x minus x cubed over 3. Alternating sum. Remember alternating sum of all the powers divided by all the numbers. Okay, etc., etc. Now here we assume x value is bounded, its absolute value is bounded by 1. So when x is 1, this is still valid. Okay, now we integrate. So arctan x over x, then we get we divide by x. This will be 1 x cubed divided by 3. So it's 3x squared over 3 plus x power 4 to the 5 minus x7 minus x6 to the 7, etc., etc. Now integrate both sides. Now we integrate. Now this is, we integrate the right side termwise. So it's the odd denominators, that's odd numbers, okay? Let's use n 2n minus 1, n from 1 to infinity, okay? Now the numerator is now decreased by 1. Don't forget the alternating factor, n minus 1, n minus 1. Okay, now we actually integrate this. We integrate it term-wise. N from 1 to infinity, -1 to the power n minus 1. Now, remember when we integrate, we use power rule, okay? Power rule. So this actually 1 over 2 minus 1. Now the power of x is 2 minus 2. It increased by 1. Increase by 1 and then divide. We increase by 1. 2n minus 2 increase by 1. So we get 2n minus 1. In x power increase by 1. Okay. And plus constant c. Plus constant c. Plus constant c. So this will be -1 to infinity. -1 to infinity. -1 to the power n minus 1 over 2n minus 1 squared times x power 2n minus 1. Okay, plus constant c. Okay, now you see if we do -1 to 1, yeah, okay, let's just leave it as it is. Now, if you want to integrate, you can try to if x here x value is bounded by 1, If x value is bounded by 1, this is actually a reasonable thing to do approximation. This is a reasonable expression to do approximation. All right. Let's see more examples. Try to transform certain functions in terms of power series. Example. Give more examples. More example. This example. Find the power series. Representation of the following functions. Representations, following functions. So let's see this example. Fx is 2 over 3 minus x. Okay, remember when we deal with power series, when we deal with geometric series, a r a minus 1. This is the 1 over a minus r. A over 1 minus r. R absolutely less than 1. And from 1 to infinity. Now, we will try to use geometric series, some of geometric series actually to explain power series. Okay. Now here is you compare this, the denominator is 1 minus r, and here this is 3 minus x. So we don't have 1. So what we do is we try to create this as 1. So we write the thing as 2 over 3 times 1 minus x over 3. Okay. Such that you see we have 1 minus r. So you write as this is the 1/3 times 2 over 1 minus x over 3. Okay. So 1/3 is constant. So here this is the, you think it as 1/3 a over 1 minus r. If you compare, you get a is 2, r is x over 3. Then you expand it. So this is the 1/3. This is the first factor first. A is 2. And then r, x minus x over 3, a minus 1. n from 1 to infinity. Okay, so if you do it simplify a little bit, so this is the 1/3 times 2 times x to the power n minus 1 over 3 to the power n minus 1. So this will be here n from 1 to infinity. So this will be 2, now 3, now 3 1/3 times 1 over 3 to the power n minus 1. So this is 3 to the power n from 1 to infinity. Now don't forget the terms. Okay, so you get a power series representation of of this function f. Okay, now the radius of convergence, the ratio, common ratio is bounded by 1. So x of value is bounded by 3, and then you find the x value, the radius, the interval of convergence, x is bounded by 3 and -3. Radius is 3. Okay, radius is 3. Radius is 3. So interval of convergence. So interval of convergence is -3 to 3. Now the radius r is actually 3. Okay, more examples. Y plus x over y minus x. Okay, now what we do is we know how to do this. 1 over y minus r. Okay, we can use geometric series r is less than 1 to expand this. Okay, now we can use this as 1 over 1 plus x split terms, x over the thing. Okay, so you see this is the first one is geometric series with the common ratio x. First term is 1, so it's 1 times x to the power n minus 1, n from 1 to infinity. Oh, sorry, yeah, n from 1 to infinity. Now the second one will be x times common ratio x to the power n minus 1, n from 1 to infinity. Okay, so this will be n from 1 to infinity x power n minus 1 plus n from 1 to infinity x to the power n. So if you write down the terms, so this will be 1 plus x squared plus x cubed, etc., etc. Now this will be x plus x squared plus x cubed plus x4, etc., etc. Now if you switch order, you see combine x with x, you get twice x. Combine x squared with x squared, you get twice x squared. X cubed with x cubed, so you get twice x cubed plus twice x power 4, etc., etc. So we get the power series representations. Okay, so it's 1 plus twice x power n from 1 to infinity. Okay, to determine the radius of convergence and the interval of convergence, remember r, the common ratio is actually x. X should be bounded by 1. So this means x is bounded from 1 to -1. So the radius of convergence is 1. Radius of convergence. Now the interval is -1 to 1. R equal to 1. Interval of convergence. Interval of convergence is actually -1 to 1. -1 to 1. Okay, more examples. Example. Ln 5 minus x. Find the power series representation of this thing. Remember we did the ln. We have ln, negative ln 1 minus t is t plus t squared over 2 plus t cubed over 3, etc., etc. So this is the t to the power n over n from 1 to infinity. Okay. Okay, or we have this ln 1 plus t. This is t minus t squared over 2 plus t cubed over 3, etc., etc. So this is the alternating sum, t to the power n over n, negative 1 to the power n minus 1, n from 1 to infinity. Okay, so here we always ln 1 plus t or something. So here we have ln 5 minus x, which is not 1. We don't have 1. So what we do is we try to factor a 5 such that we have 1. So this is actually ln factor 5, 1 minus, and then we use the property of ln. The property of ln. Remember, ln a times b is ln a plus ln b. Okay. Use this property, we can actually write the thing as ln 5 plus ln y minus x over 5. Okay. Now ln 5 is a constant. That's ln 5. And then the second formula, the second we apply the power series representation for ln 1 plus t. Okay, take t to be negative x over 5. Then from this equation, take this t to be negative 1 over negative x over 5. So this will be negative x over 5 plus minus negative x over 5 squared plus negative x over 5. Okay, don't forget this 2 cube, etc., etc. Okay, to make this more precise, you use sigma notation. To use sigma notation, this is n from 1 to infinity, negative 1 to the power n minus 1. Now t is negative x over 5 to the power n over n. Okay, now if you simplify it a little bit, so this will be ln 5. Now this will be plus n from 1 to infinity. Now here negative 1 to the n minus 1, negative 1 to the power n. Now x to the power 5, x to the power n, 5 to the power n. And then, of course, multiply by 1 over n. Okay, so the alternating factor, negative 1 to the power n, multiply negative 1 to the power n minus 1. Actually, you get all the powers of negative 1. So you got actually, this is the odd. This is odd. Okay, n from 1 to infinity. This is n times 5 to the power n, x to the power n. Okay, then we are done for this problem. So the right side is power series center at 0. Okay, the right side is power series center at 0. So when we do derive this interval over convergence, we assume this is less than 1. Okay, so we get x x is bounded by 5. X is bounded from positive 5 to negative 5. Okay, now we also need to check what happens at the boundary. If x is 5, then you see the series will be ln 5 minus. Now 5 is undefined. The series is ln 5 minus x is undefined at 5. As x approaches 5, it can be arbitrarily large, negative. Okay, so it's undefined when x is 5. You see from the power series, if you still plug in 5, then what you get is 5 to the power n, n to the n times 5 to the power n. So it's ln 5 minus n from 1 to infinity. 5 to the power n cancel 5 power n. So you see, you get ln 5 subtract the harmonic series. Okay, the harmonic series can be arbitrarily large, so this is actually negative infinity. Okay, this is negative infinity. You see, this is again undefined. This is again undefined, so it diverges at 5. I use a function undefined at 5. If x is negative 5, then it's okay. Then if x is negative 5, then it's okay, because in this situation, if x is -5, if you plug in x by -5, and from 1 to infinity. Now 5 to the power n, cancel 5 to the power n. So this is actually equal to ln 5 minus -1 to the power n over n. So this is the alternating sum of reciprocal of integers. Okay. Remember, alternating sum of reciprocal of integers. This gives us ln -2. Sorry, negative ln 2. So this is actually ln 5 plus ln 2, which is a ln 5 times 2, which is ln 10. Ln 10. Okay. Now, if you plug in the original function here, original function fx is ln x, ln 5 minus x. If you plug in, take x to be 5, -5, then you get f -5 is again ln 5 minus -5. So it's again ln 10. So it's valid when x is a 5, a -5. So the radius of convergence is you know, the interval of convergence, interval of convergence is -5 is okay, but +5 is not. So it's closed at a -5 and open at a +5. Okay. The radius is actually r is actually 5. R is actually 5. Now you need to be careful. You know, here I also check the function value at -5 and the function value at -5 and the series, the value of the power series at -5. Okay. If the power series converges, even if the power series converges at the boundary, sometimes the value that the power series converges may not be the same as the function value. Okay, at the boundary it can be really bizarre, so you need to be careful. Okay, now let's do some more example. Let's do one more example. This example. Find the power series of this ln 1 plus x minus 1 minus x. Okay. Now, use the property of ln a minus o, ln a over b is ln a minus ln b. So we can write this as ln 1 plus x minus ln 1 minus x. Okay. The number ln we for x bounded by 1, we have this power series representation of ln 1 plus x. Power series, okay. So it's x power n over n, -1 to the power n minus 1, n from 1 to infinity. Now negative ln 1 minus x. This is actually x plus x squared over 2 plus x cubed over 3 plus x power 4 over 4, etc., etc. Now we add these two above equations. Add the above equations. Then we get ln 1 plus x minus ln 1 minus x. This will be, now you see, if we add the terms, you see all the terms, x and x, they just remains. And then x squared, negative x squared, they cancel out each other. Okay, even terms cancel out, odd terms remains. So we get a twice x odd terms x cubed over 3. Now x power 4 cancel out, etc., etc. So this will be ln 1 plus x, use the property of ln. This we get twice. You know, if you write alternating sum, you write sigma notation. So all the powers you write as all the powers, and from 1 to infinity, x to the power 20 minus 1. Okay, then you are done. Okay. Now this power series, we often use this power series to compute a series that converts fast to ln 2. Remember ln 2. Ln 2 is what? Now, when you study some radioactive decay material, then you actually, to determine its half-life, then you will use the number ln 2. Now, to solve for ln 2, we take this thing to be 2. Then we get 1 plus x is twice 1 minus x, which is the 2 minus 2x. Then you solve 3x is 1, x is 1/3. We did this several times. Okay, then you see ln 2, plug in, take x to be 1/3. Then you get the left side, ln 2. 1 plus x over 1 minus x will be 2 now. The right side will be, if you plug in x by 1/3, so 1/3 cube over 3 plus 1 over 5, sorry, 1/3 to the power of 5 over 5, etc., etc. Now this power series converts reasonably fast to ln, you know, converts a little faster than the alternating sum of reciprocal integers. Now you can compute a little bit the approximation, how good this is. If you use the first, we have maybe 1 minute. So the first term gives us 2/3. The next term gives us 2/3 plus 1/2. This is the 81. Okay, so this will be 1/2, 1/3 plus 1 over 81. So you get this is 1/2, 2781 plus. So you get 2. Okay. Sorry, it's 2. Sorry, it's 2. What I did, it's 2. It's 2 here. So you get actually 56 over 81. You can check how good this approximate is. Use a calculator. Okay, so ln 2 is approximated by 56 over 81. Of course, if you use more terms, you can get better and better approximation. Okay, maybe let's just stop here for today.